I'm Dr. Karl, coming to you from the lands of the Gadigal people of the Eora Nation. I acknowledge Aboriginal and Torres Strait Islander peoples as the first Australians and traditional custodians of the lands where we live, learn and work. G'day, Dr. Karl with part 2 of Marcus Chown and his fine book, A Crack in Everything. Look, welcome back to the microphone, Dr. Marcus. So you are a real doctor. You have a PhD in...
I'm not. No, I didn't. I was at Caltech. I spent a couple of years there. I got a master's degree. My office mate, who's from Chile, it took him 35 years to get his PhD.
And you've written all these fine books on quantum mechanics. You've been my go-to guy on that. And this one now. So we got up to these jets coming out of black holes. But can we just dive into Einstein and Podolsky, mid-1930s? Because they did stuff on black holes.
They did. About wormholes, actually. I mean, there were two things, really. The really interesting thing about that is, I think it was 1935, two papers came out, and you might think, well, Einstein did all his work, finished in 1915, didn't do anything important, but of course Einstein was a great thinker. We look back
at great ideas.
We look back at these two papers and we think, there's something interesting there, because first of all, he never believed in quantum theory. So that, even though quantum theory basically describes the world around us,
and it's essential and it's real, the fact that it doesn't work with relativity is irrelevant. Don't worry about it.
Well, he realised that it had this property called non-locality. You know, if you were two atoms together and separate them, you could do something to one of them, and the other one would react instantaneously.
Yeah, you say in your book that he was a big believer in local and he didn't like non-local, so how could something 2 light years away have something happen to it instantly when something happened to the one right in front of you right here?
And that was the EPR paper. That's and Einstein, Rose and Podolsky. Yeah. And he was able to show if quantum theory is correct, then there would be this instantaneous influence.
Which turned out to be yes, indeed.
He thought, so ridiculous, it must mean quantum theory is wrong. Fast forward to about 1980, and Alan Aspect in Paris, he does an experiment with photons, what we call the polarization or the spin of photons. He separates two, he does something to one of them, the other one reacts. The only way it could have happened if something travelled at 4 times the speed of light between them.
4 times the speed of light. So they had measuring stuff that good back then.
Aspect got the Nobel Prize about a year or so, 2 years ago, something like that.
Okay, what about the other paper, Einstein, Rose and Bridges?
Yeah, well, that's interesting because it turns out that black holes are a solution to his equations, but also so are wormholes. So these are shortcuts through space-time. You know, the names are fantastic, and for that we can thank John Wheeler, who was the supervisor of Richard Feynman. He came up with the term black hole. He borrowed it from a student in his lecture. He also invented the term wormhole, which is a shortcut through space-time. We now wonder whether there isn't a connection. You know, we have a suspicion that space-time has some kind of structure, you know, some microscopic structure. We don't have a quantum theory to tell us what that structure is.
Hang on, say that again. We don't have to tell us about the structure of space-time.
Yeah, which will be what we call quantum gravity.
The physicists have been covering up from us.
I mean, if you zoom in on space-time with a super microscope, it will become more and more turbulent. You know, so in Einstein theory, the space is rather like the smooth surface of the ocean. When you zoom in, you find it gets more turbulent and choppy and all that sort of stuff. And when you get right down to what we call the Planck scale, which is this where basically we have no picture. We think that it may even have miniature wormholes connecting.
They call them Einstein, Rose and Bridges, and I think the phrase, and please correct me if I'm wrong, was that they said that these objects, the hypothetical objects that have infinite density, and here comes the 3-word phrase, are not singular.
Yes, we don't believe they are.
They're not singular, which means they're connected, and then how they connected these Einstein, Rose and Bridges may be... At this stage, you're puffing your cheeks.
If we could zoom in, if we could zoom in on a scale that is enormously, fantastically smaller than an atom, we would see it very choppy, and we may see lots of miniature kind of wormholes connecting vastly separated places. And so, bizarrely, that may allow the connections between faraway places. So these two papers that were published, which no one really thought were connected, they now say the theorem, it's not been proved, is that ER equals EPR. So in other words, could it be that the wormhole structure of space-time down at the really tiny scale is allowing the influence to go from one part of the universe to another.
Oh my God, you mean it could be solving this spooky action at a distance, which Einstein hated?
Shall we mention the Cygnus X1?
Yes.
Because Australians really need to know about Louise Webster, because she has been entirely written out of the history of science.
What?
And she discovered
Hang on.
black holes.
She's been written out? Who is the patriarchy, I say? Redress the wrongness here. Take it away, Marcus.
So Paul Murdin was English, and he'd been at American University in New York, and he came back to the Royal Greenwich Observatory in 1970. It was actually in a 16th century castle called Herstmonceux Castle with a moat around it.
So glad you said that, because when I read that, I thought to myself, how do I pronounce this stupid thing? How do you pronounce it again?
Herstmonceux.
Okay, but it's got X's and
and
stuff in it.
And when he'd been a graduate student, he was about 30 in America. He'd talked to the other students, and they thought, well, how do we make a name for ourselves? You know, because he didn't have his post at the Royal Greenwich Observatory was only short term, and he had 2 young boys. He had a family, and he came to the conclusion that the problem you've got with stars is that how do you find an interesting one? Okay, so there's more stars in the universe than there are sand grains on all the beaches around all the continents.
Roughly the Avogadro number. 10 to the 21, 23, ballpark figure.
So how do you find an interesting star? So he thought to himself, if it emitted X-rays, it'd be interesting. X-rays are emitted by matter at millions of degrees. And in the early 1960s, there had been the first X-ray telescopes which had been launched on sounding rockets. You know, they'd gone up in the atmosphere.
They stayed there briefly.
Briefly, yeah. Come back down again. So fortunately for us, the atmosphere absorbs X-rays. So they'd taken... they had brief glimpses, and they found these mysterious X-ray sources. But these telescopes were crude, and they could only say, there's one in the constellation of Cygnus or whatever, Cygnus X1. But by the time he got to Herstmonceux, the first X-ray satellite had been launched, Uhuru.
Yes.
Yeah, and he got the catalogue, and he noticed that the box around Cygnus X1 had shrunk, and there was one interesting object. It was a blue supergiant star orbiting nothing.
Orbiting nothing, you point out in your fine book entitled A Crack in Everything, which people should rush out and buy. There was this supergiant orbiting nothing.
And it was a massive star, like maybe 50 times the mass of the Sun.
50.
Something like that.
And orbiting nothing, though.
Orbiting nothing. He thought to himself, it can't be that star because it's not hot enough. It needs to be millions of degrees. Does it have a companion? Could it be that material is being sucked off it onto an invisible companion, swirling down?
Invisible companion, you say?
And this is where the Australians come in, because he was sharing an octagonal turret room office with Louise Webster. And she'd been working in America as well. She was about a year old, she was about 31. And she was working on a project to measure the speed of stars. Okay, and as you just pointed out, when we hear a police siren come towards us, it's a higher pitch. When it goes away from us, it's a lower pitch. And there's an analogous effect with light. You know, you get a higher pitch of light is bluer, a lower pitch is red. So if this blue supergiant was orbiting something, it would periodically be coming towards us, higher pitch, and then going away from it.
Yeah.
So he asked her to do it. Herstmonceux was the 2.5 metre Isaac Newton telescope, which had been built in the worst possible place, East Sussex, fog, clouds all the time.
It was an optical telescope.
Optical telescope. It would be eventually.
Why would they do that?
Eventually, they moved it to the Canary Islands at a greater cost than it actually cost to build it in the first place.
Right.
So she went away, and she found it was orbiting something every 5.6 days.
It was orbiting something that could not be seen. And yet it weighed much, much more, 30, 40, 50 times the mass of our sun, but it was orbiting nothing. Oh my God, Marcus, what could that nothing be?
Well, they worked out that the only candidate was a black hole. They thought it had to be more than 4, maybe more than 6 times the mass of the Sun. Today we know it's 15. Problem was the Royal Greenwich Observatory had been run by the Navy, the British Navy, until a few years before, and they were super cautious. You know, black holes were considered to be like magic. They didn't want to get egg on their face, so it was a real struggle to let Murdin and Webster publish a paper.
Publish it?
Yeah.
What?
So it turned out that they published and that was 1971. And really, this story connects to me because in 1971 I was a member of the Junior Astronomical Society. My dad took me to a talk by Paul Murdin, and it blew my mind. You know, the first black hole. And it blew my mind. So it was a great joy to be able to interview Paul Murdin and give him the credit he deserves. But then I discovered that, in fact, he co-discovered this object with Louise Webster. Sadly, she went back to Australia. She had one of the first successful liver transplants in Australia. And then she unfortunately got cancer and she died in Paddington, which is a suburb of Sydney, isn't it? Age of 49.
She was 49.
Yeah, and she's been completely forgotten. Louise Webster. 4 Nobel Prizes for black holes now. No one even mentions her name. When quasars were discovered, it was realised they were part of a kind of a zoo of different, what we call active galaxies. Mm-hmm. So active galaxies was defined as those who most of their light is not coming from stars.
Oh, really? I never realised that. So an active galaxy is one in which most of the energy is not coming from
stars.
Really?
It's coming from a super hot accretion disk around a black hole. So at this point we could think, oh, well, they're not very important. You only find them in 1% of galaxies. They can't be important. Then Hubble comes along. Hubble's launched in 1990 with the telescopic equivalent of a squint. Cost $800 million to fix it. It was the most complex space astronaut mission ever. Mm-hmm. And they effectively put correcting lenses in front of all of its instruments.
And it worked.
Yeah. So the problem we have on the surface of the Earth is we look up through the turbulent atmosphere, and it's like lying on the bottom of a swimming pool looking up at lights on the ceiling. They wave backwards and forwards. So they blur out. But of course, above the atmosphere, Hubble had super sharp eyesight, and in the centre of pretty much, it looked at maybe dozens of nearby galaxies, and in every single one, in the very centre, the stars were whirling around far too fast.
Because that was the discovery that virtually every galaxy was host to a supermassive black hole.
So they should be flung off into intergalactic space unless they were in the grip of a very, very dense, massive object.
Massive, say, not just the mass of the sun, but millions.
So our picture of these objects changes completely. We suddenly realise that the reason we only see 1% of galaxies active is because 99% of galaxies, they're starving. They've run out of food. They're slumbering. So they've swallowed all the material in their surroundings, and there's nothing more to eat. So they're all quiescent. So there's a supermassive black hole in every galaxy, but in only 1% are they being fed.
Okay, I'm going to take my little notepad here, and I've written down, way back then, Marcus, you said that black holes made us possible. How did black holes make you and me and the human race possible? Or to be more specific, the black hole in our galaxy.
Yeah, so my book is really about how they come in from the cold. They were ridiculous, and then gradually we realise they're more and more important, and they are connected to us being here and having this conversation.
How are they connected?
In the galaxies with the really big black holes, they tend to have these oppositely directed jets that come out of the poles, material many times the mass of the sun ejected a year at nearly the speed of light. These jets stab outwards across millions of light years of space, and they can literally, in the galaxies with the big black holes, these jets can drive away all the gas in the galaxy.
What the potential stuff of new stars.
So they snuff out star formation very quickly.
Hang on. If you've got a galaxy with big fat jets coming out of the north and south poles of the spinning black hole, that tends to snuff out, to stop, to bring to a halt star formation.
So you only get one generation of stars.
You only get one generation of stars?
Because there's no more formed.
There's no more fuel.
But in our galaxy, because we've got a tiddler, and we'll get onto that, it's a mysterious...
It's only 4 million. No, not none of this billion times, it's only millions.
It's 4.2 million. Oddly enough, it's called Sagittarius A star, and it was discovered exactly 50 years ago this year, so 1974.
And we're talking in the last quarter of 2024.
It's inexplicably small. So if you take Andromeda, which is our companion galaxy, very, very similar to ours, spiral just like ours, its supermassive black hole is 50 times bigger than ours.
What? 50? So ours is 4 and it's about 200.
Yes. So we've got no idea why we've got such a small black hole, but because it's so small, it's never had these powerful jets. They've never pushed away the material
that's necessary for the next generation and then the generation after that.
So the sun is a third generation star. So basically stars have formed, exploded, the material has filtered out into space and it's become the raw material of the next generation. The key thing you need to know is that in each successive generation, more of the heavy elements, the calcium, the carbon, the iron, elements which are essential for rocky planets like the Earth and for biological life like ours, have been built up. In the galaxies with the big supermassive black holes, they are living deserts. There can't be any planets, there can't be any life. But in ours, because of this ridiculously, inexplicably small supermassive black hole,
a lousy 4 million times the mass of the sun.
So we are here because of this tiny black hole.
Thank you for answering that question. In your later chapters, you talk about where we go philosophically. So I'll just say a little tiny thing. You tell me how wrong I am. 4 of the big mysteries are dark matter in physics, dark energy, the missing dimensions of the universe, and black holes. And I'm kind of thinking that in a century, at least one of them will be solved. By the end of this century we're in, I say, by the time we get to 2100, at least one of them will be solved. I'm guessing, are you going for dark matter to be the one solved first?
I think maybe black holes, because we are learning things week by week. So you mentioned the James Webb Space Telescope, which was the successor to Hubble, launched, I think, about Christmas almost 3 years ago.
And it can look visible and infrared, which is an extra advantage.
Yeah, because as the universe expands, it's been expanding after the Big Bang, the light kind of gets stretched in wavelengths. So it becomes redder, and so we need to look in the infrared to see the early universe. And it is absolutely blown everyone's mind, because we're looking back to maybe when the universe was maybe 2% of its current age. Mm-hmm. And we are seeing galaxies which are far bigger than anything we expected.
We had expected. And by the way, remember the old saying, is it true or did you read it in the Daily Mail? So whenever you see a headline come through on your smartphone saying, oh my God, the latest findings prove that everything we know about the universe is wrong, don't believe it. We're just tweaking things.
Yeah, there's galaxies that are much more massive than we thought, much brighter than we thought.
And so early. Like 400 million years after the Big Bang itself.
Some of them have got supermassive black holes that are almost 1 billion times the mass of the sun.
How did they get so big so quickly?
That is the real key question.
Hang on, I'm asking you, you're asking me. That's wrong.
That is the key question. So either you have a very large seed to start with, mm-hmm. and then you suck in more material.
So you just accumulate matter like crazy.
One of the problems with sucking material in a fast rate is there's a thing called the Eddington limit. So the accretion disk becomes so bright that it
pushes away.
So we must start off with large seeds. Now, we don't actually know how those seeds formed, but maybe some exotic processes in the Big Bang spawned the seeds of these supermassive black holes. And I think we might get the answer within the next few years.
What? In less than a decade? So my little dream that somebody will be saying in years to come, hey, Jacinta, stop playing with the black hole and come in and have lunch, might possibly be the situation in some decades from now.
Yeah, because the thing about dark matter is we have no hint of when we're going to crack this problem. I mean, we've been looking for 40 years in earthbound experiments and we've seen no sign of it. We've got no idea what it is. Black holes, we know they exist. We can see them out there. We got the first ever image in 2019, a globe-spanning array of telescopes called the Event Horizon Telescope got a picture of the supermassive black hole in the centre of our galaxy.
And you talk about that in your book in one chapter where I think they got like 1 ton or 5 tons of hard drives gathering all the data from radio telescopes around the world, and they brought them all together.
That's right. Yeah. I mean, it's an amazing technique to do that. But we are very, very fortunate in this technique will just about allow us to see, because remember, the bigger the telescope, the finer the detail you can see. Resolution. And we're very fortunate in this supermassive black hole. It might be relatively small by cosmic standards, but it's only 27,000 light years away. And there's another one in a galaxy called M87, which is 6.5 billion times the mass of the sun, which we can see. So I think, black holes, they're incontrovertible, whereas dark matter and dark energy, we haven't got a clue what it is. We haven't got a clue.
So we know they are real.
It's probably real.
Almost certainly real, or probably.
Well, the evidence we find everywhere we see, for instance, stars in the galaxies orbiting far too fast, they ought to be flung off into intergalactic space. So we postulate that there has to be a lot of invisible matter whose extra gravity is holding on to them. I mean, it's conceivable that there's something wrong with Newton or Einsteinian gravity.
And we've got the modified Newtonian theory.
But that's a very complicated thing
and it doesn't cover everything.
Well, there's something badly wrong. And certainly if you see things moving far too fast, that faster than Newton would have predicted, the simplest theory would be to say there was some modification of Newton's theory on these large scales. But I don't know. I mean, on the other hand, it's quite possible that there are subatomic particles that do not interact via light or electromagnetic force. I mean, we certainly find like neutrinos, they are ghostly particles. If you hold up your thumb, 100 billion are going through your thumbnail every second. They come from the sunlight generating nuclear
And they
reactions.
change from one form to another along the way.
Yeah, so they don't interact. They only interact by what we call the weak nuclear force and by gravity. So it's quite entirely conceivable that there are other particles that don't interact via light and therefore are dark.
Now, this is your book, and how many books have you written?
I've written quite a few.
Okay.
I think I've written about 20.
You've written 20. So Marcus Chown, that's your name. A Crack in Everything is your latest book. How black holes came in from the cold and took cosmic centre stage. And how can people follow you and your magnificent work and buy books and let you give you enough income to write another book?
Good question. So I've got a website and it's www.marcuschown.com.
CHOWN,
Yep. You can follow me on Twitter. I'm called Marcus Chown, and my books are available in Australia as well. And in fact, my book was published at the beginning of October this year.
October 2024. Look, thank you so much for blowing my mind again, Marcus, and I look forward to doing it all again with your next book.
Thank you very much.
Shirtloads of Science is washed, spun and aired by the University of Sydney.